In this video, we're going to look at a couple of examples that are not specifically in the other videos, but are just slight extensions of what has already been taught. So the first is an improper integral of a different form, and the other is the root test for testing convergence of infinite series. So let's start with this improper integral question. So here we have an integral that we want to test to see whether it converges, and if it converges, to evaluate that integral. Now you'll notice that neither of the limits are going to infinity or negative infinity. However, there's a vertical asymptote at x equals 1 because the denominator will be 0, and there's a limit at x equals 1. So there's an asymptote anyway. Even though there's not a horizontal asymptote, there is a vertical asymptote that we have to worry about. So that's the place where this convergence is going to be in question. So our first step is to rewrite the integral, obviously, instead of a 1 over radical, to write it as x minus 1 to the negative 1/2, and then to acknowledge the fact that this lower limit here of 1 is where the asymptote is. We create a limit as a approaches 1 from the right-hand side, because that's the direction that the integral, the interval of on the integration is happening, of that function with the a on the lower limit in this particular case. Now again, any variable is fine, but I like to go a and b, so in this case a is the lower value. So we take the integral, and of course, this is just a quick reverse chain rule, so it's 2x minus 1 to the 1/2, and then of course it's being evaluated between a and 2 with that limit as a approaches 1 from the right-hand side. So now I substitute my 2 and my a over here, and I subtract. And then I notice that I can evaluate this because 2 minus 1 is 1, 1 to the 1/2 square root 1 is just 1, so 2 times 1 is 2, so there's my 2. And then I rewrote this a minus 1 to the 1/2 as a square root. It's not necessary, but I did it anyway, so I'm still doing this limit. Now again, it's important that a is coming in from the right to 1, because otherwise this would not be defined for real numbers. But since we're talking about values larger than 1 coming in, something larger than 1 minus 1 is positive, and therefore this is an acceptable real number, and therefore, again, as the pattern for a going closer and closer to 1, that limit is going to go to 0. So I end up with 2 minus 0, which is 2, and of course I can say the integral converges to 2. Now again, if I could not evaluate this limit, or I was going to get infinity or something like that, then I would say the integral diverges, but in this case it converged. So now we're going to talk about the root test for testing the convergence of a series, and you will recognize here that the root test is appropriate because it's blah 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 to the n. You can do the ratio test on a lot of these, but it's much more complicated. It's much easier to use the root test if you recognize that that's available to you. So a quick reminder about the root test. So you do the limit as n approaches infinity of the nth root of the absolute value of an of course being the term in the series. If that limit is less than 1, then the series converges. If that limit is greater than 1, then the series diverges. And if that limit is equal to 1, then the test is inconclusive and you have to try something else. So of course here an is 2n plus 3 over 3n plus 2 quantity raised to the n, as previously stated. And of course the fact that it's raised to the n is our clue that the root test might be appropriate. So here I do the nth root of the absolute value of an. The absolute value is really not important because as n goes to infinity, this is all positive, so we're fine. And of course when you do the nth root raised to the n, those cancel out as well, again positive, because we're talking about very positive n values of n. So this becomes that limit. So I use my clever little trick where I multiply the top and bottom by 1 over n to get this limit instead. And of course, when I evaluate, as n gets larger and larger, these two terms go to 0, so this is just 2/3. And of course, because that limit is less than 1, the root test says that the series converges, so I say sigma blah 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 converges by the root test, because you want to specify what test you used. And that's the end of this video.